If I say P3, for P3, as you know, P subshell has 3 p orbitals, right? And since it has 3 electrons, so fill these 3 electrons according to Hund's rule, right? So each degenerate orbital will get 1 electron each with the same spin. Either you can write this way, or you can fill these 3 electrons like this way. Both are the same thing, no difference in them, right? Both way is permissible. Okay, now number of exchanges here. Number of exchanges of the position of electron will be, you can see here, this electron can exchange its position with this and with this. So number of exchanges of this electron will be 2, and number of exchange of this electron will be 1, because this electron can exchange its position with this electron only. So for this electron, number of exchanges is 2. For this electron, number of exchange will be 1, and for this 0. Therefore 2 plus 1, 3. Therefore for P3, number of exchanges will be what? 3. Similarly, if I say P6, so how can you fill? First, each p orbital will get 1 electron with the same spin, and then pairing of electron will start with the opposite spin. So here you can say number of spin up electron is 3, and number of spin down electron is also 3. A spin up electron will exchange their position with another spin up electron, and a spin down electron will exchange its position with another spin down electron. Remember here, a spin up electron cannot exchange its position with a spin down electron, right? So number of exchange of a spin up electron will be 3, and number of exchange of position of a spin down electron will also be 3. Therefore total number of exchanges here will be 6. Therefore you can conclude P6 will be more stable than P3, because in P6 number of exchanges is 6, and in P3 number of exchanges is 3, and therefore further it is proved that fully filled up subshell is more stable than half filled up subshell, right? So I hope you got the concept of exchange energy, right? Now another explanation for Hund's rule is, symmetry. Symmetry, right? Remember here, symmetry leads to the stability, right? Symmetry means if each degenerate orbitals of a subshell has same number of electrons, then you will say they are symmetrical. Like if fully filled up subshell or half filled up subshells are there, then they will be called they will have symmetry. And symmetry, since symmetry leads to the stability, therefore you can say fully filled up subshell and half filled up subshell are more stable due to their symmetry also. If I say D5, so then all the 5 d orbitals have same number of electrons, therefore you can say they have symmetry. But if you say D6, fill the electrons, 6 electrons according to Hund's rule, like this way. Now here one d orbital has 2 electrons and other 4 d orbitals have 1 electron each. Therefore, you can say it is not symmetrical. Now, you have seen earlier it, in case of d5, number of exchange of position of electron is 10, and in d6 also, number of exchanges of the position of electron is 10. In both d5 and in d6, number of exchanges is same. Therefore, d5 will be more stable than d6 because in d5 there is symmetry. So you can say, you can conclude it, symmetry leads to the stability. If an orbital has symmetry, then it will be more stable. Remember this, and therefore you can say fully filled up subshell and half filled up subshells are more stable due to their symmetry also, right? Now, the third explanation is a spin. The third explanation is a spin multiplicity. The third explanation is a spin multiplicity. A spin multiplicity is calculated by using this formula 2s plus 1, and here s is total spin of electron, right? For example, take the example of d4. D subshell has 5 d orbitals, and here there are 4 electrons. So according to Hund's rule, you will fill these 4 electrons in this way, all with a spin up or all with a spin down. It is the same thing, but remember here all electrons should have the same spin, right? Now, this electron s, that is a spin quantum number of this electron, will be plus half. This will also have plus half. This will have plus half, and this will have plus half. Therefore, total spin here will be half plus half plus half plus half, that is 2. So, a spin multiplicity for d4 will become 2 into, and total spin is 2, so 2 into 2 plus 1, that is 5, right? Now listen one thing. More the spin multiplicity, more will be the stability of the subshell, right? I mean, that subshell will be more stable which has maximum spin multiplicity. But here remember one thing, don't use the concept of spin multiplicity to compare the stability of two different subshells, right? This concept of spin multiplicity is used in case of a particular subshell having a fixed number of electrons. For example, if I say I have to fill 5 electrons in D5, that is, I have taken the case of D5. Therefore, how many possibilities can be there to fill 5 electrons in 5d orbitals? So one possibility is fill all the 5 d orbitals with single electron each with the same spin. One way is this. Another way is one electron spin up, other spin down, one spin up, another spin down, and one spin up. The third way may be in this way. This orbital 2 electron, again 2 electron, and 1 electron. I mean, if I say about D5, so there can be so many possible arrangement to fill these 5 electrons in 5d orbitals, but we have to select which arrangement will be permissible, which arrangement will be more stable. Then we have to find a spin multiplicity for all these arrangements, and that arrangement will be permissible, will be valid, which has maximum spin multiplicity, and that arrangement will be according to Hund's rule, and therefore it is said Hund's rule of maximum spin multiplicity. For example, if I say D5, so here total spin will be 2 and half, 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 and half. That is 2 and half. So for this, spin multiplicity will be 2 into 2 and half plus 1. This will come to be 6. Okay. Now, for this, spin multiplicity will become, for this spin up electron, spin quantum S will be plus half, and for this minus half. Plus half minus half 0. Plus half minus half 0. For this plus half. So here total spin will be plus half only. So this is half, 2 into half plus 1. So spin multiplicity will be 2. Again, find a spin multiplicity for this arrangement also, right? This is a spin up, so for this S will be plus half, and for this S will be minus half. Plus half minus half 0. Plus half and minus half 0, and for this plus half. So for this total spin is half, so 2 into half plus 1. For this also spin multiplicity is 2. Now look, among these 3 arrangements, which arrangement has maximum spin multiplicity? Then you will say this, because its spin multiplicity is 6. So this is permissible, and this is according to Hund's rule, and therefore the name is Hund's rule of maximum spin multiplicity. Now, as I said earlier, a spin multiplicity is not used generally to compare the stability of 2 different subshells, right? Suppose if we have to compare the stability of D5 and D6, then don't use a spin multiplicity for that. If we have to compare a spin multiplicity, stability of D6 and D7, then don't use a spin multiplicity concept there. A spin multiplicity concept is used in a particular shell having particular number of electrons, and suppose I am saying D7 or D8. Right, you have to fill 7 electrons in 5d orbitals. So there can be so many arrangements to fill 7 electrons in 5d orbitals, right? So you fill in different ways and find the spin multiplicity of all this arrangement, and you will see that arrangement will be permissible, that arrangement will be according to Hund's rule, which has a spin multiplicity maximum, right? Now arrange the stability of some subshells. For example, if I say a stability of D5 and D4, out of D5 and D4, which is more stable? D5 is more stable than D4. Now, reason. We can give two reasons for this. D5 is half filled, so it is symmetrical. But D4 is neither half filled nor fully filled, so it is not symmetrical. And in neighboring cases, symmetry leads to the stability, as you know. So due to symmetry, D5 is more stable than D4. The second reason is, in case of D5, number of exchanges of position comes to be 10, and for D4, number of exchanges of position of electron comes to be 6. So D5 is more stable than D4 due to symmetry, more symmetry, as well as more number of exchanges of the position of electrons. Similarly, if I say stability D5 and D6, which is more stable out of D5 and D6? Obviously, D5 is more stable than D6, and reason for this is only symmetry, right? Because in D5, as you calculated earlier, number of exchanges is 10, and in D6 also number of exchanges is 10. Therefore, exchange energy concept is not applicable for this. For two different subshells having different number of electrons, or for two same subshells with different number of electrons, don't use the concept of spin multiplicity. Then there is the only the explanation left, that is symmetry. So you can say D5 is more stable than D6 because D5 is half filled, so it has symmetry, right? Now if I say compare stability of D10 and D5, okay, and obviously D10 is more stable than D5, and reason behind this, only number of exchanges, because don't use symmetry, concept of symmetry here, because it is fully filled, it is half filled, and both fully filled and half filled have symmetry, so concept of symmetry can't be applicable here. But we can use number of exchange energy concept here. D10 has a number of exchanges 20, D5 has a number of exchanges 10, therefore D10 will be more stable than D5. Now look this very important example. We have to arrange the stability of P6, D10, P3 and D5. Now arrange these subshells on the basis of their decreasing stability, and the right order of their stability is this. Among these, most stable is P6, then D10, then P3, and least stable here is D5. Assume all these subshells are of the same shell, right? Now, what may be the reason here? You can conclude here, P6 is fully filled and D10 is fully filled. That is, these are two different subshells, but their condition is same. That is, both are fully filled. If there are two different subshells, but their condition is same. Condition is same means either they are both fully filled or both half filled, then you will say their condition is same. Now remember, if there are two different subshells, but their condition is same, then position of the subshell dominates over the number of exchanges. Here you will see P6 has a number of exchanges 6, D10 is number of exchanges 20, but yet P6 is more stable than D10 because P subshell is closer to nucleus than D. Remember here, in a shell, there is first S subshell, after that P, then D, and then F. And that subshell will be more stable, will have lower energy, which is closer to the nucleus. Since out of P and D, P is closer to the nucleus than D, therefore P is more stable than D. So P6 will be more stable than D10. So what I said earlier, if there are two different subshells and their condition is same means either both are fully filled or half filled, then position of the subshell will dominate over the number of exchanges. Therefore P6 is more stable than D10. Now look here, this is D10 and this is P3. This is fully filled, this is half filled. Now if there are two different subshells but their condition is not same, here in D10 and P3 you may see their condition is not same. This is fully filled, this is half filled. Then you can conclude, if there are two different subshells and their condition is not same, then number of exchange of position will dominate over the position of the subshell, right? Now in both these, number of exchanges will dominate, and obviously D10 has 20 exchanges, P3 has only 3. So here number of exchanges will dominate over the position, and so D10 is more stable than P3. Now again, in P3 and in D5, you see both have the same condition. Both are half filled. So both have the same condition. And again, these two different subshells have the same condition. Then here, position of the subshell will dominate over the number of exchanges. And since P subshell is closer to the nucleus than D, so P3 will become more stable than D5. I hope you got. Therefore, do practice of such type of questions, right?